All right, we're going to start out with chapter 9, kind of going over the book, talking about nucleophile and base strength here. First, we're going to talk about nucleophiles. Okay. All right, so up until now, we've had to be provided whether it's an SN1, SN2 reaction, or E1 or E2. Okay. That's not always going to be the case. It's usually, from now on, it's not going to be given. It's going to have your nucleophile or base, your electrophile, some reaction conditions, and it's up to you to decide, okay? And as we get into synthesis as well, this is really going to help with that. So, okay, we're going to start out with substitution, SN1, SN2. How do you decide which one to use, okay? Now, I mentioned this, I think, a week ago or so, in that straight away, if you have a, let's say you're substituting a leaving group like bromine, okay, and you have a primary alkyl halide, okay, everything's going to happen at once, it's going to be concerted, and this is always going to be an SN2 reaction when we have primary like that. There's low steric hindrance. Our nucleophile can attack our electrophile easily, and because of that, it's going to happen in one step. Okay, so every time you have a primary leaving group, it can be SN2 if you're debating on which substitution reaction to use. Okay, so primary, we can go ahead and say that's SN2. If you have something that's tertiary, like this. Now there's a lot of steric hindrance on there. It's going to help if we can get a carbocation there, free up a little room, and notice we'll have a tertiary carbocation, which is much better than what would have been before a primary carbocation. So if we can make a pretty stable carbocation and free up a little bit more room and make that carbon more accessible, especially with a large group like bromine leaving first, a tertiary leaving group is going to favor always an SN1 reaction. So we won't have to decide much if it's tertiary or primary. Most all the examples from now on are going to be secondary leaving groups. That way we can actually decide a little bit more on whether we need to do SN1 or SN2. Okay, that's a big point there. Tertiary and primary. Tertiary SN1, primary SN2. Now if it's secondary, we can go into a little bit more. Okay, let's maybe touch on that a little next video. SN1, SN2 is largely going to depend, okay, on firstly nucleophile strength. We can get into aprotic and protic solvents, but mostly it's going to be nucleophilic strength. What is a strong nucleophile? Okay, a stronger nucleophile is really one that it's going to make our reaction go by faster. Okay. Like we talked about slow and fast steps with SN1 and E1. A strong nucleophile is something that has usually has a negative charge associated with it as well. Okay, so here is what the textbook provided. I wouldn't memorize these. I would be familiar with it, kind of see some trends here. I noticed that our weak nucleophiles, water being the lowest, our weak nucleophiles do not have any explicit formal charge on them, okay? They don't have any charge. If I were just to notice a trend, I see water is my lowest, and I see I have some nitrogens with no negative charge, are weak nucleophiles, okay? Now as I go further into what are deemed strong nucleophiles, notice every single one of them has a negative charge on it. And I should say that another reason not to really memorize this is that a lot of strong nucleophiles are also strong bases. So memorizing it's not really gonna help a lot in that case. We have to decide between them. Just notice trends. First trend being our strong nucleophiles have negative charges on them, formal charges, okay? I can also see, and if that nucleophile is more, if the electrons associated with that nucleophile are more accessible, that's also a good thing. So not only do I have a formal charge, but also, are my electrons accessible to react, okay? So let's think about that. Now as I have my halides and I'm going from left to right and I'm increasing my nucleophilic strength, I have a very large iodine and I'm moving and I'm getting smaller towards chlorine. Those chlorine, it's a smaller atom, those are more accessible electrons, okay? It's not a big difference with our halides, and usually you won't have to decide between one halide and the other, in most cases. A lot of these is like, Dr. Andrews is probably gonna take something over here and something over here, and make it a little bit more obvious with that case, but are my electrons accessible, okay? So I have my halides here, very electronegative. As a group, they're gonna wanna hold on to those, okay? But because chlorine's a little smaller, okay, it's gonna be a slightly better nucleophile in that case. Especially if we're having to attack a carbon, right? Chlorine's smaller, there's lower steric hindrance when we have to react with that electrophile, in most cases carbon, okay? Moving on, now I have some sulfur species, okay, next. Notice I've gotten less. I moved one over in the periodic table, so now I'm less electrophilic, and then I'm also still lower than oxygen, so I'm a little bit bulkier in this case. But I have sulfur here, they're stronger than our halides, okay? These are just showing that these two are the same. And then I'm moving slightly from halides to sulfur to oxygen. So now I'm less electronegative than my halides, but I'm also smaller, okay? So I'm gonna continue that trend. So these electrons are more accessible because I'm less electronegative, okay, and I'm smaller here. So these are also good nucleophiles, my oxygen species. I move over again. My nitrogen is holding on to those electrons even less because it's less electronegative. So those electrons are more easily accessible here in my nitrogen-containing compounds with a negative charge. Notice if nitrogens do not have a negative charge, they are weak nucleophiles. And then I move over once again to now have carbon species that have a negative charge, okay? Less electrophilic, electronegative, that way the electrons are more accessible. Our carbon's not holding onto those tightly, they can react more easily in that case. And of course, they have a formal charge. So increasing left to right, I wouldn't memorize this, but I would notice the trends in that firstly, negative charge means strong nucleophile, and then the further you move this way in the periodic table and the less electronegative you get, the more reactive those electrons are going to be in these SN2 and SN1 reactions. Okay? We'll get to that in a second. Okay. Now I have bromine and chlorine up here, just on an energy coordinate diagram in an SN2 reaction. So which one's going to be favored, really? And we can use this diagram to help us out and look at delta G, okay? Now you might want to say that, oh, bromine is a better nucleophile because it has a lower energy at its intermediate, okay? But the case, and that your textbook mentions this, is actually you have to look at the activation energy. Which one's going to be a better SN2 nucleophile? Which one's going to be faster? Which one's going to be faster is the one with the lower activation energy. So although chlorine has a higher energy total intermediate, notice its activation energy is a lot smaller than bromine's, okay? Just relating that energy standpoint to rate, okay? It's just, your textbook mentions it. I wouldn't pay a lot of attention to it, but do know that this is down to activation energy and rate rather than starting points in here, okay? And again, chlorine is better because it's smaller in this case. So as we get smaller, usually we get better nucleophiles. Of course, these both have negative charges on them, okay? Now, make sure you can see this. Yeah. Okay. But deciding between SN1 and SN2 again. This is, okay, so I obviously have a secondary leaving group. Probably, not obviously, I probably have a secondary leaving group. All right. Now, we learned last week that the rate law of an SN1 and E1, an SN1 reaction is largely dependent on the carbocation only. Okay. Only the carbocation, okay? So no matter what my nucleophile is, no matter how much I increase or decrease that, it's not gonna matter. It's only my carbocation intermediate. So my SN1 rate is constant, okay? Doesn't matter on nucleophile strength. We just went over that big list of things, doesn't matter. It's largely only gonna matter on my SN1 carbocation that I get, because that's my rate determining step. SN2, however, varies, okay? Now, if I have, this will be in blue here. So SN1 is this pink line here, just representing that my rate is right in the middle. It's not gonna change. There's my carbocation. That's the rate determining step, okay? Whether I have a weak or strong nucleophile, doesn't matter, because my carbocation is always gonna stay right here, all right? Now, if I increase the strength of that nucleophile, now I have a really good SN2 reaction. So if I have a strong nucleophile, now I have a good SN2 reaction. If I have a weak nucleophile, I don't have a very good SN2 reaction. SN2, that nucleophile has to attack that carbon and the leaving group has to leave all in one step. So the stronger nucleophile we can get to do that, okay, the faster our rate's gonna be. But if we have a weak nucleophile trying to do all of that stuff in one step, SN1 is gonna be favored. Big takeaway, if I have a very strong nucleophile, I'm gonna do SN2. If I have a weak nucleophile, I'm probably gonna do SN1. Because if I do a weak nucleophile with SN2, our rate's gonna be very slow, okay? So, strong nucleophile, SN2. Weak nucleophile, it's actually better to get SN1, carbocation intermediate there, for the most part, okay? So, here's a question your textbook asks you, okay? Here again is our strength of our nucleophiles, okay? And it asks, you know, what do you think about H2P minus? Just throws it out. It's not on the list, just asks you straight up, what do you think? Do you think it's a strong nucleophile? Here's how I would look at this problem. First off, is there a negative charge? Yes. Pretty good indication it's a strong nucleophile, all right? Now, I have H2P minus, phosphorus. Phosphorus is in the same column as nitrogen, okay? I know nitrogen is less electronegative than oxygen, less electronegative than our halides as well. So I don't have the most electronegative atom with a negative charge. That's probably going to be a very good nucleophile, okay? So I would definitely say this is a strong nucleophile, assuming that phosphorus, of course, has similar chemical properties to nitrogen because it's in the same column. And if I look up here, H2N minus, H2P minus, H2N minus is very strong nucleophile. And if I were to put this somewhere in this, I would probably put it in this region here, okay? Because it's larger than nitrogen. Notice our larger species are usually lower here, sulfur more than oxygen, so you would expect phosphorus to be just a little bit less than nitrogen. But overall, I would say this is a strong nucleophile. Firstly, because of that negative charge, and second, because phosphorus isn't a very electronegative atom, at least compared to what else we have up here. Notice our carbon is the least electronegative atom, and it's the most nucleophilic. Whereas we keep going this way, we have a negative charge, negative charge, negative charge. Our most electronegative atoms are actually our lower nucleophiles. Okay, next we'll, actually I think I'm just gonna keep going. I'll just do elimination as well. Yeah. All right, strong nucleophiles. Negative charge on a not as electronegative atom. And then, if it's very strong, SN2. If it's weaker, SN1. It's a big takeaway, all right? All right, so let's talk about bases. Bases are a little bit more difficult to explain. Again, kind of goes back into a lot of our good nucleophiles are also good bases and vice versa. pKa's are going to help a little bit. And there's a few things I don't have up here yet. I'm gonna make another video, or I'll probably end up with 2 videos. But let's introduce this concept in this video, and then we'll move on. All right. Now up here I have increasing order, and I've made 2 rows. I ran out of room. This top row, okay, left to right, and then it moves on to the bottom row. Your textbook describes all of these in the black letters as weak bases, and all of these in the red as strong bases, okay? Again, increasing left to right. If you notice, it looks very, very similar to what our strong nucleophiles are. Halides, oxygen, fluorine's in there, but whatever. Sulfur, nitrogen, our OH group, okay, that's like the cutoff of strong and weak. We have our OH group, strong base. Everything else here is above OH is a strong base. Everything below OH is considered a weak base. So then again, I get my carbon and I get my oxygen, nitrogen, carbon species. Okay, it's extremely similar to strong nucleophiles and strong bases. So again, it's another reason why I wouldn't memorize this chart and strength order by heart. More so just the concepts. Okay. Yeah, negative charges all over the place. So here's maybe a little bit. Here's another way to think about it. Okay. Your textbook has like a ask you a question about this as well. Before we get to that, same concept in that you have 2 bases, maybe on an energy coordinate diagram. Which one's the better base? Which one is this reaction going to go by faster? Which one has the lower activation energy? Not which one has the highest energy intermediate. Which one has the lowest activation energy? Okay. Here we have OH being a stronger base than our carboxylic acid conjugate base. How about that? Okay. Notice that the activation energy for that is a lot larger than what it would be for our OH group. Okay. Just in case it shows up on the assessment, which one's the stronger base according to this energy coordinate diagram? And many people are going to be like, oh, it's the OH group because it's higher here, it's stronger, you know, it's not as good a base as this one because it's lower energy. That would be incorrect. Just look at the activation energy. Okay. So again, OH is a better base because it's a lower activation than this other species there. Cool. We also know, a few weeks back, we talked about pKa and acid strength. Okay. When we were dealing last time, we were determining largely what's the stronger acid. And that in turn also made us ask, well, what's the more stable conjugate base? Stronger acid, weaker the base. Flip it. The stronger the base, the weaker the conjugate acid. The stronger the base, the weaker the conjugate acid, the higher the pKa. Remember, our strong acids had really low pKa's, our weak acids had really high pKa's. So if we have a really high pKa, we have a weak conjugate acid of a strong base. Okay, it's just flipping all of that around. Stronger base, weaker conjugate acid, higher pKa. Acids have really low pKa's, bases have high pKa's. All right? So your textbook asks you, you have the pKa of this acid here with sulfur in it. This is it sulfuric acid? Maybe? I don't know. Don't need to know. What I do know is that the pKa of this acid is 7.4. Okay? pKa is 7.4. That's kind of strong-ish, right? Okay. Kind of. Now, okay, so the pKa of this is 7.4. Is it a stronger base than this? Okay. First, we have an acid, so let's make it a conjugate base first so we can compare these two. I would just remove a hydrogen, and I would get HS minus. Okay. The conjugate acid of this base is this here. It has a pKa of 7.4. The conjugate acid of this base is this here and it has a pKa of 7.4. The conjugate acid of this species, I have a CH3, I have a carbon here that's bonded to 2 oxygens, negative charge, okay? The conjugate acid of this would be carboxylic acid, and we know carboxylic acid has a pKa of about 4. Okay, so now we have 2 pKa's we can work with. Carboxylic acid is a stronger pKa. Stronger the pKa, lower pKa, means it's a stronger acid and we have a weaker base. Lower pKa tells me it's a stronger acid and a weaker base. Higher pKa tells me weaker acid, and better base. Okay. So I would say this is the stronger base because I have a higher pKa. Okay. On a rate of about 1,000 times better base, actually. Okay. Stronger base, weaker conjugate acid, higher the pKa. This one had a higher pKa, stronger base. Ta-da! Okay, so there's a couple ways we can kind of visualize this on an energy coordinate diagram with pKa's, because bases are kind of difficult to explain conceptually and why some are better than the others, mostly because it's very similar to why nucleophiles are good nucleophiles. Okay? So maybe just a couple more concepts with this, and then we're going to do some example problems. The example problems are going to help big time. Okay, it's conceptual stuff I know is maybe confusing at first, and it might help with some assessment questions, but really going through the examples is going to help more than anything else. Okay.